Okay, so we continue with the Fourier series. Remember, we did the real Fourier series with some examples. We clarified the geometric interpretation of the Fourier series. Then we studied the complex Fourier series. We saw the relation that the real and the complex Fourier series are both the same, but they are written in different ways. Depending on the applications we are dealing with. Also, we did the Dirichlet theorem, which allows one to substitute certain values in the Fourier series, and from that, if you remember, we found certain infinite sums. The next topic in Fourier series is what's called Parseval's identity. So what is Parseval's identity? Parseval's identity, we will see it's for our purpose in this course, we will apply it to find certain infinite sums again. Remember, we use the Dirichlet theorem, for example, to find sums like -1 to the n over 2n minus 1, if you remember. Now, with Parseval's identity, we will be able to find other infinite sums. Now, in communications and electrical engineering, Parseval's identity is a very powerful tool to find the power of the signal. So if you have a signal, communication engineers use Parseval's identity to find the power of that signal. So what is this identity? What is this identity? The idea of the Fourier series, let's say, assume that you have f of x is equal to the sum and from negative infinity to infinity Cn e to the I and x. Okay. So basically, this is like the Fourier series, right? And this is the complex Fourier series. Okay. Now we need to mention, I know that most of you did not deal deeply with complex numbers, but I is a complex number, okay? And what is I? I is the number whose square is -1. And as we mentioned before, we write I equals root -1, but we need to be very careful because when we deal with complex numbers, root -1 has two values. It can be 1 or -1, okay? Okay, so now we're dealing with complex numbers. In complex numbers, we need to remember that squaring a complex number does not give you necessarily a positive number, like this one. I square, you are squaring something, but you're getting a negative number. In the real numbers, if you have any number x and you square it, you guarantee it's positive. It's for sure bigger than or equal to 0. In complex number, this is not guaranteed. So what is the operation? What is the operation in complex numbers that correspond to squaring real numbers? So what's the operation you're doing in complex numbers that guarantees you will be getting a positive number? It is what we call the modulus. It is the modulus. So what is the idea? The idea. If you have the real line, this is the real line. This is 0. Okay. So if you take any number x, whether it's positive or negative, I think we all agree that the distance between 0 and x, in the case x is positive, the distance is x. For example, if x was 5, you measure the distance between 0 and 5, you get 5. If x was -5, for example, you measure the distance, it will be 5. But what's 5 for -5? It's -x. So if you agree, the distance is denoted by absolute value of x, because what is the absolute value of x? It's x if x is positive and -x if x is negative. Now, what corresponds to this in complex numbers is the modulus. So what is the modulus? The modulus is like R when you deal with polar coordinates. So if you have a point which corresponds to a complex number like this, 1 plus I, for example, you measure the distance from the origin. This distance is called the absolute value of the number. So it's basically the same meaning, but in the real line case, the distance is just the absolute value of x, which is plus or negative x, depending on whether x is positive or negative. Now this is a distance, which is square root of 2, right? Because this is like the point 1, 1, so the distance is root 1 square plus 1 square. Now in general, if you have a number, a complex number, so again, I'm trying to extend the square from the real line to the complex plane. So if you have a complex number like 1 plus I, what happens if you multiply it with 1 minus I? You will get 1 square plus I minus I square, which is 1 square plus 1 square, which is 2, right? Now the 1 square plus 1 square, this is exactly what you get when you apply the distance formula, because the distance formula is the root of the first coordinate square plus the second coordinate square, right? So in general, what happens is that if you have a complex number, if you have a complex number a plus bi, you multiply it with a minus bi, what do you get? You get a square plus abi minus abi minus b square I square. These get cancelled, and the I square is negative 1, so this becomes a square plus b square. But again, if you imagine AB as a point, what's the distance from that point to the origin? So the square root of a square b square. This is what you're getting from here. So what corresponds to the distance from the origin? In the real line case, it's the absolute value, the absolute value that we are familiar with. But in the complex numbers, it is the square root of a square plus b square, which is basically obtained from multiplying the complex number with what we call its conjugate. So if you have a complex number a plus bi, its conjugate is a minus bi. For example, what's the conjugate of 1 plus I? It is 1 minus I. What's the conjugate of 2i plus 3? It's negative 2i plus 3. These are basic concepts from complex numbers that I assume you are familiar with, at least from like a course like circuits, for example. Okay, if we feel we need, I can make one video for these topics, but this is not our topic anyway. We will need these computations, but this is not our topic. Okay, so back. So now I have a function, and now this function can be a complex function or a real function. I mean, so far we've been dealing with real functions like f of x equals x or x squared, or even when we dealt with piecewise functions like this and so on. All our functions take real numbers, real values. But when we deal with complex with the Fourier series, our function can be something depending on I. For example, I can have a function like x squared plus ix. Yes, this is a function. So in general, and because in the complex Fourier series, we see this e to the I, so we expect to have some complex values, right? So now I want to square the f, but my square is not the normal square, it is the modulus square, okay? So this is why I introduced the modulus. So then, if I take the absolute value of f squared, again, this does not mean the normal absolute value, because I'm dealing with complex values because we're seeing the I. So what do we mean by the absolute value of f squared? It is the function times its conjugate. It's like a plus bi times a minus bi. The a minus bi is a plus bi conjugate. The conjugate of a plus bi is a minus bi. Again, if you feel you have difficulties with this, please tell me, and I will clarify it in one video. Okay, so this is the sum, and from negative infinity to infinity, Cn e to the I nx, right, times the sum, and from negative infinity to infinity again, Cn e to the I nx conjugate, and the conjugate goes into the sum. So now you are multiplying two infinite sums. Now the point, just imagine, what is the infinite sum? It's just you're adding some stuff, right? Something plus something plus something and so on. Then you're multiplying with the same thing, plus 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 and so on. So basically what you need to do is to expand the brackets, right? So you multiply every term with everything, every term with everything, and so on. So basically, So basically, when you multiply these two brackets, what do you get? What you get is, you get the sum, so you need to multiply every term in here with everything there, right? So you will get Cn conjugate e to the I n minus mx, and what is the n? What is the n for all possible choices of n and n from negative infinity to infinity. Where did we get the e to the I times n minus m? E to the I n x is clear from here. And what about the minus m? This is the conjugate. So if you look at e to the I n x, what is this? This is cosine n x plus I sine n x, right? So if you replace this by negative, this becomes negative. But this being negative, this is exactly the conjugate, sorry. This is exactly the conjugate of cosine nx plus I sine nx, right? The conjugate of this number is that number with negative. But this is exactly e to the I nx conjugate. So when you talk about the conjugate, of e to the I nx, it is e to the negative I nx, fine? Okay, so now imagine, and please be very careful here, you can't use n for both. So you can't say here Cn and Cn conjugate. The reason is, for example, you have C1, okay, plus C2 plus C3, just imagine this, times the same thing, C2, and so on. So you're talking about the sum of Cn times the sum of Cn. Now when you multiply, the C1 should be multiplied with C1, with C2, with C3, right? So the C1 should be multiplied with C2, with C3, with C4. So the C1 should be multiplied with Cm for all possible values of m. The same for C2. The C2 should be multiplied with everything. The C3 should be multiplied with everything. So in the end, you will be adding the sum of all possible choices, Cn times Cm. That's why we need to change the n and the m, okay? Okay, so now what is this? This is just an infinite sum. You're multiplying all these quantities together. Now this is just a step that we need to look at the integral from minus pi to pi f of x squared dx. So what is this? This will be the sum, because you can distribute. Okay, we have lots of details about when we can switch the integral and the sum, but let's assume that we can take the integral into the sum. So we have the integral, the Cn and the Cm, these are constant. So basically you have the integral from negative pi to pi e to the I n minus m x dx. This is what we have. Now what about the integral from minus pi to pi e to the I n minus m? We did this before. We did it somewhere when we dealt with this example exactly. So remember when we found the complex Fourier series of this function, we had to deal with integrals like this, 3 minus n, 5 minus n, and we explained all these steps, and we said these integrals will always give us 0 as long as the 3 minus n or the 5 minus n are not zeros. This was our condition, if you remember these details, okay? So the idea in general, so now we're integrating e to the I n minus mx dx from negative pi to pi. So if we do the integral here, so if you say integral from minus pi to pi e to the I n minus mx dx, what is this? It's the same thing over I n minus m from minus pi to pi. But I'm sure now everybody is saying, okay, this is not true if n was equal to m. So this is true only if n is not equal to m. Okay, so what happens when n is equal to m? We need to do it again. Okay, so what is this? you substitute the pi, you substitute the negative pi, so this is n minus m pi minus I n minus m pi over I n minus m. But we computed these values before. Both are negative 1 to the n, and this is 0. Just to remind you, when you compute e to the I k pi, k is integer, okay? If k was integer, when you compute this, what is this? This is cosine k pi plus I sine k pi. What is cosine k pi? It's negative 1 to the k, and sine k pi is 0. So basically this is negative 1 to the k. So that's why when you compute, sorry, here I have a typo. This is n minus m, this is n minus m. So whenever you have e to the ik pi, you get negative 1 to the k. My k, in my case, is n minus m. So this is why this integral is always 0 when n is not equal to m. So now the question, because in your formula, you have the sum from negative infinity to infinity, but for all possible values for n and m, which means it is possible that n is equal to 1 and m is equal to 1. It's possible that n is equal to 2 and m is equal to 2, negative 1 and negative 1. So these values are not calculated by this integral, because this integral doesn't work unless n is not equal to m, right? So now the point is, I need to look at what happens when n is equal to m. I need to do it. So when n is equal to m, I need to look at the integral from minus pi to pi e to the I n minus m x dx. But if n was equal to m, this integral becomes e to the I0, which is just 1, which is what? Which is just 2 pi. So now we go back. We look at this formula here. We say this integral, the integral square, the integral of f of x squared dx is equal to the sum, the infinite sum of all these integrals. But after doing all these integrals, we found them. All of them are zeros. Except when n and m are equal. So when n and m are 0, then you have 2 pi. This is what we found, right? When n and m are 1, then your integral is 2 pi. When n and m are 2, then your integral is 2 pi. So basically what happens is, when n and m are equal from negative infinity to infinity, you're getting what? You're getting cm conjugate times 2 pi, which is 2 pi times, but if n is equal to m, then you don't need to say n and m, you just can say n from negative infinity to infinity, and in that case you'll get cn times cn conjugate. But what is cn times cn conjugate? It is the absolute value of cn squared. So this is it. This is Parseval's identity. I just need to summarize it. So after doing all the computations, we reached that this integral is equal to this value. Okay, so I'm just doing it like this. So the summary is, so Parseval's identity, if f is periodic of period 2 pi, then 1 over 2 pi integral from minus pi to pi f of x squared dx is equal to the sum from negative infinity to infinity cn squared. Okay, so this is the summary of Parseval's identity, and I'm sure at this stage you can expect what happens if the period was 2L. I'm sure that everybody sees it, right? So this is 1 over 2L integral from negative L to L f of x squared is equal to the sum from negative infinity to infinity cn squared. Okay, so this is Parseval's identity. This is it. We need to somehow to memorize it. Let's see a few applications of this identity. And please, this is the complex version of Parseval's identity. What do we mean by the complex version? I mean, I started with the complex Fourier series and found this Parseval's identity. But what happens if you start with the real Fourier series? Then yes, you have another form of Parseval's identity. The two forms are equivalent. We'll see them, okay? We'll see them. Okay. So before saying the real Fourier series, the real Parseval's identity, let's see an example on how to apply and what is the nice application of Parseval's identity. So let's recall that I think we solved one example about the integral. This is it. Yes. So we looked at this example. The function is x. The function is x. Then we found the complex Fourier series. We did all these computations. In the end, in the last line, we found that the Cn is equal to this thing, okay, and the C0 is 0. So in the end, we found that the Fourier series is equal to this form here, okay. This is the final form of the complex Fourier series of x. So recall that for f of x equals x from negative pi to pi, we found that the Fourier series is the sum when n is from negative infinity to infinity avoiding 0 minus 1 to the n over n I times e to the I n x. Okay. Now in this example, I just want to show you how to apply Parseval's identity. So the first thing, I need to understand the Cn's. So in this example, what are the Cn's? These are the Cn's, but we need to be very careful, okay? So this means that C0 is 0 because this summation runs over all indices except for 0. So when n is 0, C0 means the coefficient of e to the 0 I0x, which is the constant term. In this example, I don't have a constant term, so C0 is 0. Otherwise, so if n is not 0, what is the Cn? Then the Cn is negative 1 to the n over ni. Okay, so I need just to see this. Okay, so now if we apply Parseval's identity, so applying Parseval's identity, what do we get? What is Parseval's identity? Parseval's identity says, of course, you can read it both ways. The sum of all Cn square is 1 over 2 pi integral minus pi to pi f of x squared dx, right? Okay. So now let's look at the Cn. So what is the Cn again? This is the formula for Cn. So we're saying that the sum n from negative infinity to infinity when n is not 0, because again when n is 0, C0 is 0, it doesn't count, it doesn't contribute to the sum. Absolute value of minus 1 to the n over n I, this is the Cn square, is equal to 1 over 2 pi integral minus pi to pi. What is f? It's x squared dx. What is this? This is the sum from negative infinity to infinity when n is not 0. Negative 1, when you square it, it becomes 1. The n, when you square it, becomes n squared. The I, when you square it, and we need to be very careful, it's not only the square, you have the absolute value of I. So what is the absolute value of I? What do we mean by I? I is the number, the complex number 0 plus 1i. So basically the absolute value is the root, is 0 squared plus 1 squared, which is just 1. So this is it. So the minus 1 to the n, when you square it, the minus 1 to the n, when you square it, you get 1. The n, when you square it, you get n squared, and the I gives you 1, so it vanishes in this case. Okay, so what is this equal to? This is equal to 1 over 2 pi, and you just need to integrate the x squared. The x squared is x cubed over 3 from negative pi to pi. Okay, now what do we mean by the sum? Of course, we can leave it this way, but let's simplify to see something, I think, something interesting. So you're adding the square of all reciprocals, right? So you're taking the reciprocal of all square of positive numbers, positive and negative numbers. So it's like this. When n is 1, you're taking 1 over 1. Then when n is 2, 1 over 2 square, 1 over 3 square, 1 over 4 square, and you go to infinity. But this is done also on the negative side. So when n is negative 1, you have 1 over negative 1 square, which is 1, and 1 over negative 2 square, which is 2 square, 1 over negative 3 square, which is 3 square. So basically this sum here to the left, it is double this, right? This value. So the left sum gives you exactly the same as the right sum. So I'm going to write this as, so the left side here is 2 times the sum from 1 to infinity, 1 over n squared. What is this equal to? It's equal to 1 over 2 pi, and when you substitute the pi, it gives you pi cube plus another pi cube. So basically, you will have, so 2 times the sum from 1 to infinity, 1 over n squared equals 1 over 2 pi cube over 3. Now the 2 is cancelled, the pi is cancelled, and if you divide by this 2, what you get is that the sum from 1 to infinity, 1 over n squared is what? It's pi squared over 6. It's the 3, and you divide it by 2. So we reached this very nice formula. So applying Parseval's identity in this example gives us the sum of 1 over n squared. That's equal to pi squared over 6. So if you understand what we are saying, in calculus 2, you dealt with this series as a p series. This was a p series with p is equal to 2. That means it's a convergent series. But in calculus 2, you didn't do any method that tells you the sum of this infinite sum. Okay, it is convergent, but what is the sum? What is the sum? We don't know it. Now we know it. So the sum of all of these squares is pi squared over 6. This is one of the very nice applications of Fourier series, and in particular Parseval's identity. And I think that we found this sum when we dealt with the function x squared and the Dirichlet. So if you go back a little, I'm sure we will see it somewhere. So these are the notes. This is complex. So before the complex, yes, let's go back to the function x squared. I hope we did it. Okay, yes, this is it, right? We found it. So this is it. The sum of 1 over n squared is pi squared over 6. How did we find it? We used the function, not x. We used the function x squared, and we applied the Dirichlet theorem, right? Remember, this is our example. This is our example here. So the function that we were dealing with is x squared. We wanted to apply the Dirichlet theorem, and after applying the Dirichlet theorem, we reached the sum 1 over n squared is pi squared over 6. This is a very nice, it was a very nice application of the Dirichlet theorem. Now please, what we are saying in the new example now, today, we are saying don't use Dirichlet like before, use Parseval's identity, and you get the same sum. So please, I'm going to write just a little remark. So the function x squared, we applied Dirichlet, we got the sum from 1 to infinity, 1 over n squared is pi squared over 6. The function x, we applied what? We applied Parseval's identity, we reached the same conclusion. Later I will show you in general how we think of this stuff. It's not standard. So if I give you like an arbitrary sum, it's not so easy to find it using Fourier series. But for these standard sums, I will show you in general how we think about them, and how do we decide if we want to apply the Dirichlet theorem or Parseval's identity, and which function do we select. Okay, so this is this remark. Okay, so in this example again, I wanted to show you the significance of Parseval's identity, and we did, I think. that we found the sum of 1 over n squared that's equal to pi squared over 6. What about if we take the function x squared? If we take the function x squared, we can make this in another video, but if we take the function x squared, we apply Parseval. If we take the function x squared and we apply Parseval, we will not get 1 over n squared. We will get 1 over n to the 4. And again, we need to understand these ideas very well before doing anything. So before proceeding to the x squared example and other examples, I think it's good to look at very special and simple cases like, for example, let's find the integral from minus pi to pi e to the 2ix minus e to the 3ix plus e to the minus ix squared dx. Okay, so I want to compute this integral. And again, because of the I, when we see the absolute value here, this is not the standard absolute, this is not the real absolute value, this is the complex absolute value, which measures the distance between the complex number and the origin. So the idea, if we substitute, if we let f of x equal this thing, without the absolute value, without the square, okay? So I think you all agree that C1 is, or C2 is 1, C3 is negative 1, C negative 1 is 1. These are the coefficients, okay? So C2 is the coefficient of e to the 2ix, which is 1. C3 is the coefficient of e to the 3ix, which is negative 1. The same for C negative 1. And all other c's are zeros, if you agree. Okay? So the idea is, okay, so I know that Parseval's identity, it says that the sum from negative infinity to infinity absolute value of Cn squared is equal to 1 over 2 pi integral from minus pi to pi absolute f of x squared dx, right? So from this, if you look at the integral from minus pi to pi absolute value of f squared, that's equal to 2 pi, the sum from from negative infinity to infinity Cn squared. And this is exactly what we want. What we want is this integral. But this integral is exactly this because we substituted f as this. So if you substitute this as f of x, basically what you wanted to compute is the integral of the absolute value of f squared. And this, of course, reminds everybody of Parseval's identity because this is what Parseval's identity is about. It is about the integral of f squared, relating it to the sum of all the squares of the c's. So now that's it. So now I say, okay, this is equal to 2 pi times, what are the c's? All the c's are zeros except C2, C3, C negative 1. So basically you take the absolute value of C2 square, the absolute value of C3 square, C negative 1 square, and all the other c's are zeros, so we don't write them, and that's it. So this is equal to 2 pi times, what is C2 square? 1, C3 square is 1, and C negative 1 square is 1, so the final answer is 6 pi. So this integral, in the end, it's equal to 6 pi. This is like the easiest computations that you can ever see using Parseval's identity. Now, if we don't use Parseval's identity, so if, let's say, if you give this question before seeing Parseval's identity, how would we solve this question? It's really complicated. It's not easy at all. So I'm not solving, okay? I'm just telling you what happens if we don't use Parseval's identity. So without Parseval, what happens? You need to look at e, what are these things? It's e to the 2 minus e to the 3 plus e to the negative, right? I want to compute the modulus squared, the absolute value square of this function. Now, as a complex number, to compute the absolute value square, you need to write it as something plus I times something. This is, okay? And then you say, okay, this is a square is equal to the first square plus the second square. This is how we compute the modulus square of a complex number. So the idea is that we need to simplify this. So what is e to the 2ix? It is cosine 2x plus I sine 2x minus, what's e to the 3ix? It's cosine 3x plus I sine 3x plus, what's e to the negative ix? It's cosine x minus I sine x. Then you collect all the cosines because those terms do not have an I. Then what is with I? It is the sine 2 minus the sine 3 minus the sine, okay, like this. All of this square. Then this is equal to the square, sorry, without the square root, then this is equal to the first quantity square. Just imagine what's going on. So you're talking about this square plus this square. Then you need to expand the brackets. Then you need to integrate from negative pi to pi. This is taking too long, right? So this is the advantage of applying Parseval's identity. If you don't use Parseval's identity, if you don't understand Parseval's identity and when to use it, then you are really in trouble with when you're stuck in these computations. Okay, so this is the idea, and again, this is the advantage of Parseval's identity. Again, I'm going to call this the complex Parseval's identity, and let's see now the real version of Parseval's identity. So what is the real, I mean, if we use the real Fourier series, so now if we take f of x as a node plus the sum from 1 to infinity an cosine nx plus bn sine nx as the real Fourier series, then so what is Parseval's identity in this case? It is 1 over pi integral minus pi to pi f of x square dx equals 2a node square, sorry, I'm going to write it in general, so I need to use the absolute value again, plus the sum from 1 to infinity absolute value of an square plus bn square. Now, how do we get this formula? It goes exactly in the same way as we got the complex Parseval's identity. Remember, we did these computations, we multiplied the function with its conjugate, we simplified until we got into the summation. If we apply the same ideas, but in this case we will need to do integrals among the sines and cosines, then we will have this formula. This is called the real Fourier series, okay? I think you should try proving this identity. You should be able to do it after seeing at least the proof of the complex form of this identity. So now let's see again what happens in the previous example here. We applied, in this example, we applied the complex Fourier series on the function x, and we found the sum of 1 over n squared. Let's apply the real Fourier series to the same function and see what we get. So again, let's take the function x as our function, and let's apply, I just want to apply Parseval's identity. Okay, if you remember, the first example in this chapter about the Fourier series was finding the Fourier series for this function. It was the sum from 1 to infinity to negative 1 to the n plus 1 over n sine nx. This is the real Fourier series of the function x. Okay, so please again, I want to look at the sum and understand exactly what this term here is, 2, negative 1, and so on. This is the coefficient of sine nx. If you compare this with the real Fourier series, Bn is the coefficient of sine nx. So basically this is what? This is exactly Bn. Okay? So what is An in this case? An is the coefficient of cosine nx. But in my example, I don't have any cosine. I don't have any constant term. So here, I think we all agree that A0 and the Ans are all zeros, but the Bn is 2 times -1 to the n plus 1 over n, right? So if you apply Parseval's identity, what does Parseval say? Parseval's identity say, this is it. Parseval's identity says this thing, exactly. So if the A node is 0 and the An is 0, then how do you read Parseval's identity? You will say, okay, the sum from 1 to infinity, absolute value of Bn square is 1 over pi integral minus pi to pi of x squared, right? That's it, because the A's, all the A's are zeros. So basically this means that the sum from 1 to infinity, now what is the Bn? This is the Bn. If you square it, the 2 gives you 4, the -1 is cancelled, it becomes +1 over n squared equals 1 over pi, and what's the integral square? It is x cubed over 3 from -pi to pi, right? Which is basically 1 over pi to pi cubed over 3. This is just a standard integral. If you cancel the pi with the pi, you will have 2 pi squared over 3. So basically, please, what you have is, in the end, this sum is equal to this value. So if you divide both sides by 4, you will be left with the sum from 1 to infinity. You'll be left with the sum from 1 to infinity, 1 over n squared. When you divide the right side by 4, you get pi squared over 6. So you're getting the same sum again. So please, what was the idea of this example? Before this, we used the complex form of Parseval's identity on the function x. This was our function x. We applied the complex Parseval's identity. We found the sum of 1 over n squared. Then, after doing the real Fourier series, we applied the real Parseval's identity. We applied it on the same function x. We got the same sum. Again and again, the real Fourier series and the complex Fourier series, they are the same, but they are written in different ways. The complex Parseval's identity and the real Parseval's identity, they are the same, written in 2 different ways. If you simplify one form of the Parseval's identity, you will get the other form. I mean. Now in this page here, we've written the real form of Parseval's identity, and when I wrote this form, I told you the proof goes exactly the same way as before. I said you just look at this f of x, you multiply it with itself as before, then you need to do some integrals. But the other way to do it, remember, we have some relations between the Cn's, the An's, the Bn's. So if you go back to the complex form of Parseval's identity and you replace every Cn with its value in terms of An and Bn, if you remember, we had these relations before. Let me remind you. So if you go back to the complex Fourier series, the first thing we did on complex Fourier series, this is what we had, if you remember. So this is the relation between the Cn's, the An's, and the Bn's. So again, if you take these values, so you replace every Cn with its value in terms of A node, An, and Bn, and plug that into the complex Fourier series, which is here. If you replace every Cn with its value, then you will get exactly this form. This is very nice. So again, the two identities are the same, but written in different ways depending on our application. I encourage you, because I didn't do these computations, but I encourage you to do both proofs for the real Fourier series. So first, prove it in the normal way. I mean, just multiply the function with its conjugate and do all the integrals. The other way, replace the Cn's, as we just mentioned, in the complex Fourier series by their values, and see what you get. So this is the idea of Parseval's identity. I think I will try to do more examples in coming videos.